Hey, Precalc. I'm so excited that we have another AMI day, especially on one of our most important lessons yet. I wish we could just hold off on it, but we do have a pretty strict time schedule in terms of pre-calc trig and stuff we have to cover in a decent amount of time before things start getting crazy. Anywho, thanks to everyone that brought some questions to the Google form. It was very helpful, and I'm glad the majority of you guys are getting it. Speaking of which, if you know someone that hasn't filled out the Google form, because there's quite a bit of people in pre-calc that haven't, in other words, if you have friends and you think they may have not filled it out, get on them about it, because it will accept it still. It'll still be an AMI attendance thing, and they're quiz points, and those are harder to come by. Speaking of which, we will be having a partner quiz on Thursday. Hopefully, we'll be back Wednesday, but tomorrow or Wednesday, I do plan to go through a lot of word questions with you guys. I actually have made a worksheet this weekend about it, so yay. You notice you have 3 questions on your Google form, so be on the lookout for those 3 questions throughout the vid. Anywho, here I want to go through a question from 5.2. It was a requested one. It was number 16. It was given that you have an area of 134 feet squared of a 240-degree sector, find the radius. So here are the 2 formulae you have. You have S equals R theta, and A, your area, is equal to 1/2 R squared theta. Now, you have to make sure your theta is in radians, okay? So you have to convert your degrees to radians before you even start doing anything crazy about that. So firstly, let's convert 240 degrees to radians. So we know that, and we need our degrees to cancel. So 180 degrees is pi radians. So then you got 240 over 180, degrees cancel, times pi. So now we're just left with 4 pi over 3. You divide top and bottom by 60. So 4 pi over 3. And actually, once we actually start getting into the trig part of things, so we're going to have a lot of degrees, radians, and degree conversions. So it's going to be in a very good habit to start picking up on some patterns, especially when we hit this thing called the unit circle. So there's a lot of memes about it. But anyway, that's step 1. So convert that to radians. Next up, we need to take our area formula, and we need to solve for R here. So we've done quite a bit of these, especially during the literal equations stuff, and those were very helpful. We've done quite a bit of these specifically. So here, in order to solve for R, we need to multiply the 2 over, divide by theta. So now you got 2a over theta is equal to R squared. Now we need to take a square root, and usually you'd want to introduce a plus or minus square root, but here we can't have a negative radius. Usually it tells you your orientation, so you just take the positive root. And now you just plug it in. So 2 times 134 divided by 4 pi over 3. Make a cute change, flip it, take a square root, punch that into your calculator, and you should get a number. Now I'm lazy and I don't want to do it, but the answer is online, so if you plug that into your calculator and didn't get the answer that's on there, it's sorry. But it should give you a nice clean number. Anyway, that was it from 5.2 that I wanted to go through. Now, one of the questions I want to go through, one of your Google form questions is going to be a challenge, actually. So here's going to be question number 1. Now, the astute individual would have picked up on something about these 2 formula here. Now, if you notice, an arc length, so given a circle, like this, the arc length is simply this little divot here. We're trying to find the arc length. It's that little distance there. Now, that's the formula for arc length. And how many radians are in a full circle? So there's 2 pi radians in a full circle. So 2 pi. And the arc length of a full circle has got a very fancy word for it called the circumference. And that's got a formula of 2 pi r. Notice that. So that's a very astute thing to do. You can also do something very similar with the area formula. So hopefully this blows your mind if you haven't already picked up on it yourself. But there are 2 pi radians still in a full circle. Now here, the 2's cancel out. The 2 and the 1/2 does. So now you're just left with pi r squared, which is a very nice formula that we've probably seen 1,000 times. Now, why did I just pick up on that part specifically? Well, let's talk about what a cylinder is. Now, cylinder, this thing right here, it's like a can-looking thing. Something like that in 3D. Got a circle, and there. The surface area formula for this is actually 2 pi r times h. That looks familiar. And that would be the surface area. That would be the area of this whole thing right there. In other words, your arc length kind of shot down like that, plus 2 pi r squared. This is surface area, 2 pi r squared, which that's the area of the circle on top, and the area of the circle on bottom, which is pi r squared plus pi r squared equals 2 pi r squared. And that's how you get the surface area of a cylinder. Question 1 in the Google forum is, what would be the surface area of a cylinder cut in half like that? So given this kind of thing. If I can draw it, oh my word. So if you were to just chop this cylinder in half and just take this little chunk right here, actually, I'll just take this. What would be your surface area of this? Meaning your half cylinder, and then it's just kind of cut there. Your objective is to find out what that surface area formula would be. That's question 1 in your Google forum. What is the surface area of a cut in half cylinder? Question 1, good. Now, the actual meat and potatoes of this video isn't going over area and arc length. It's actually continuing on to 5.3. I truly wish I would have given you 5.3 homework, but I did not foresee that we would be stuck here on a Monday, or a Tuesday actually, in your places again. Let's go over the notes. So the idea behind this is that we're looking at speed now, not velocity, because I put little arrows there to indicate velocity. And that's just me being technical and being very nitpicky about things. So linear speed is distance over time in general. Now, angular speed or angular frequency, we're going to be looking at that very specifically, is theta over time, meaning how many angles you're going over time, versus linear speed would be how fast you're going in a straight line almost. Now, there's a lot of connections between the two, and there's a lot of nuance behind it, and it's hard to get kind of cut down in the nitty-gritty. But actually, there is a nice little converting formula given to us here, where this is not W. This is actually a lowercase omega. So it's a Greek letter once again. W is usually, I draw a little bit more straight like that, while omega is kind of a little curvy. There's a slight difference between the two, but that is what angular speed is going to be. That's going to be the, not the formula, but the symbol for it. Now, this is a very important formula to get down. V equals R omega. We'll be using that quite a bit to convert between the two, because we're going to look at some examples, especially word questions about all of this stuff. Now, one of the word questions I want to go through with you guys is actually not from the notes, but it's from the homework. I have the homework keys posted, so look at 5.3. I just have the answers for it, but I want to work through a very specific one with everybody. And that's going to be number 6 from homework 5.3. So pause the video and look at the notes for the homework sheet for that. I haven't passed it out on paper, which I'm kind of reluctant to do now, but I want to look at number 6 because it's a tougher question. And I'm going to walk you through how to do this and how my method's pretty nice for it. So firstly, let's look at number 6. It's about a bike. So firstly, you have a 12-inch radius for your wheel, and it's going at 175 RPM or revolutions per minute. We want to find the linear speed in miles per hour. There's something really cool about these is this is actually the math behind speedometers. Because back in the day, how would you determine how fast you're going? Well, they didn't have GPS in your they really didn't have GPS in your cars back in the day. So in order to do that, they just did this conversion and programmed it. Now, how do you even approach this? Well, firstly, you want to find omega. And omega is typically in radians per second. We have revolutions per minute here. And actually, we probably want it just in radians per minute, to be honest, because that's going to be a little bit easier. So in order to do that, we know that one full revolution, being one time around a circle, is 2 pi radians. Now here, I use the fence post method, and that's what I did on all the note questions, because the fence post method is what helps me out with it. So firstly, you have 175 revolutions divided by 1 minute. Because in 1 full minute, you do 175 revolutions. And here, we want to create this fence post. Now, what is a fence post? Well, each of these vertical lines are multiplication, while the horizontal lines is known as division. So, in order to get our units right, we want to make sure our units cancel out. In order for them to cancel out, you need to have them on opposite ends of your division bar. So here, we want to have revolutions cancel. So we do 1 revolution on the bottom. We know that it's going to be 2 pi radians. So there we go. And here, you get your revolutions to cancel because they're on top and bottom, because this is division. And they're just like numbers, right? They're just like variables. Units are just variables, if you really think about it. So now, in order to actually do the conversion, you do 175 times 2 pi divided by 1 times 1, which is just 1. So, and that's going to be under minutes. So now you have 350 pi radians per minute. Now, how do we know if you want to actually punch that in and get a decimal approximation? Pretty much you want to do that at the end, because it's going to be very helpful for you. And we want this in miles per hour now. So in order to do that, well, we got to do some more fence posting. So V equals R omega is also a valid way to go. However, in order to do that, we can actually kind of sneak that in with our fence post. So we have a radians per minute right now. We need miles per hour. So here, we'll set up another fence post. So radians per minute. Now, miles per hour. So we know something about the radius here. We actually know the radius. So in order to do that, we can multiply it, because a radius and a radian are intertwined. So in 1 radian, you know that it's going to be equivalent 12 inches. Just because that's the definition of a radian, and that's like a ghost unit almost. So we have our radians canceled. So now we got inches per minute. There's well, we have to keep going now. So we need to get miles on top. We need to get hours on the bottom. So here, we probably just want to do the minutes right now, just to get that out of the way. So last time I checked, there's 60 minutes and 1 hour. So now we have hours on the bottom. And that's exactly what we want, because the word per means divide. So that's just miles over hours. So yeah, perfect. Now we got inches per hour. So now we got to convert the inches into miles. I don't know the inches to miles off the top of my head, but I do know that there are 12 inches in 1 foot. So now the inches are canceling. Actually, the 12s cancel too, which is super nice. And then now we got feet on top. We want feet, or we want miles on top. So 5,280 feet, of course. We all know that is in 1 mile. So now we have miles on top, and all the other units are canceled, and we got hours on bottom. So now we want to do 350 pi times 60 We would have done times 12 and then divide 12, but we actually kind of figured out that they cancel, which is very convenient. Times 1 times 1, so that's it for the top. Then you got 1 times 1 times 5,280 on the bottom. 5,280. And now we can actually punch this in the calculator with pi, because here it doesn't really matter. Well, it's not really going to be helpful if we keep pi with us, because we actually want an approximate answer. So going through this and punching this into the calculator now, we end up with, let me see, I have it here somewhere. Donde está? There we go. Messed up. 12.5 miles per hour, which is a reasonable answer, MTH. Because if you got something like 100, bikes don't go that fast, really. They usually go about 12.5 miles an hour-ish. So that's a great answer, actually, to have. Yeah, question 2 on your Google form. What questions do you want to go through from the 5.3 homework? I just want you to write down which one from that assignment. Because I don't know if I actually want to give it as an assignment now. I just might give it to you as extra example questions, because I have something we're going to go through in class on Wednesday. But yeah, no, pick a question from the 5.3 homework and put the number down and what it's going over. Maybe even write the question out too. And that's going to be question 2 on your assignment. Now, this fence post method, I learned actually not necessarily in math class. I actually learned in science and physics, because you do a lot of converting like that. You can't just punch this into Google and do conversions that way. No, that's not how it works. In fact, I would like to even let you use a calculator on it for that reason. Because whenever we do it in quizzes and tests, there's very specific things that MACC wants me to do without a calculator. Teach you how to do it without that. Now, obviously here, we actually had to approximate with a calculator. But sometimes can't really use that. So you'll need to know how to do this fence post method, or some sort of conversion method that suits your fancy. This is just kind of nice, structured, and convenient way of keeping track of everything and organized. Because lo and behold, that was a lot of converting, because we actually had there's more to it too, because we want to do it all in one fell swoop and put the revolutions and radians in there. You could have also done it that way. Regardless, that's kind of the way to go about it. I'd say go through the notes, look through some of the examples and see if they make sense. Try them out on your own too. And actually try out some of the homeworks too. If you're really thinking about like, oh no, I'm stressing. Because we do have a partner quiz on this stuff on Thursday coming up. So in order to get a leg up and get ahead, that'd be an excellent thing to do. Now, question 3 on your Google form. Answer the following. How are you guys doing? I like being at school. So doing this whole virtual stuff kind of is pretty trash for me. I'm a very social person, so it's a lot on me. So how are you guys doing? Let me know how your new 5-day weekend now is. And yeah, keep up the good work, and let me know if you have any questions. Office hours will be tomorrow. Stop in if you have any questions that you want to go through. I'll be chilling. So, yep. See ya hopefully on Wednesday.